Okay, welcome back. So, hopefully you've just finished setting up your model and your system is all valid and everything's working perfectly. Now we're going to do our optimization. So, we're going to have you optimize the geometry of the cross sections of the pipes that you're going to use. You are also able to change the geometry of the bike itself. So in order to achieve that, you might click on the point and then go here and make that a parameter. Just make sure that whatever you're changing in your point geometry, it stays valid according to the Excel spreadsheet I gave you at the start. If it changes a little bit, so maybe a few millimeters here and there is probably not a big issue. I don't mind too much. A clever hint might be to keep your seat tube aligned with the y-axis and tilt the rest of the bike according to that. You'll need to do a trig transformation on the spreadsheet I've given you in order to achieve that. What that means is you can just move that seat tube up and down nice and easy. So, let's go into our optimization. So to bring in an optimization, we go to Response Surface Optimization. It is possible to do a direct optimization, but it is very computationally expensive and quite annoying. So you just take this guy, drag it in, and that is going to share the parameter set that I've generated in these two. So you go to Design of Experiments, and we look at all the parameters that we have access to. Design of Experiments, Input Parameters, and Output Parameters. So I'm just going to preview, and that should give me all of the valid parameters that we're going to use for this analysis. Okay, and so there we are. Now, there are 150 different design points. That's going to take about 3 to 4 hours to solve, which is not ideal. So I recommend that for your first optimization, you have just 2 different parameters, which will give you 12 points, which will solve in a few minutes. So, what we'll do then is we'll solve this. Just going to look at our input parameters. So, an important thing for you to know is how to change your input parameter restraints. So, here's the right chainstay wall thickness. And if, for example, I want to have that between 0.5 millimeters and 2 millimeters, I set it here. So I go to Input Parameters, select the thing that I want to change, and it's always a good idea to set your bounds nice and wide. So remember that clicking this Update button is going to solve the solution surface, and the preview will tell you where all the points are going to fall. So if you're just sussing it out, just click the preview button, don't click the update button, because the update button will take a very, very long time to do anything. If you click the update button inadvertently, just spam the hell out of the abort button. So a progress bar will come up down here, a green progress bar, and then to the right of it, it may or may not show, but there should be a red abort button, and just spam the hell out of it until you actually get to abort. So, let's look at an optimization I've prepared earlier. So here's our design of experiments, and it has solved all 148 possible points. That took about 4 hours, and it's given us all of those possible solutions. So then what you do is you go to your optimization. So you'll solve your response surface, and then you'll go into your optimization. And the optimization takes that information and it will find an optimal solution. So what we do is we go into Objectives and Constraints, and you go into, I'll show you how to do it from the start. So we go Objectives and Constraints, select a parameter, and I want to minimize the mass of my system, geometry mass. I want to minimize the total deformation maximum, and I want to minimize the maximum combined stress. So my objective is minimize, my objective is minimize, minimize. And then you can set a constraint. So for example, you want to have your stress less than 80 megapascals. So this is my stress, less than equal to upper bound. and then my upper bound here is going to be 80 megapascals. So it's nice and within the fatigue limit of steel. Then you're going to click Update and solve it, and that will allow you to run your optimization. A quick point, which I glossed over before, is that if you want to have the mass of your system, you go up here to Geometry, Properties, and then click Mass. And that'll allow you to have a mass parameter in your solver. So that's in the solution part, not the design modeler part. Okay, so then we go back to our optimizer, and you'll solve it. It'll take however much time it takes, and it will give you candidate points. Now these candidate points show you where the optimal outcome of your geometry is. In this case, so let's look through. So I've got a mass of 3.3, 3.4, 3.3. I've got a maximum deformation of 2.1, and so I think I have actually told the computer that the deformation is less important. The deformation is more important than the mass. So, thinking about bikes and how they work, do you want it to be more stiff or more heavy? That's up to you to decide, but I want you to use this decision support process. So you're going to go here, and you're going to choose the objective importance of, say, changing the mass, the deformation, and just make sure that you've got a hierarchy of objectives. So you're going to solve that, and then we're going to look at our trade-offs. So that one looks particularly good. These are our samples, which just kind of shows you the solutions as we go through. And then the sensitivities, which I mentioned in the very first video, and it shows you how much effect each of your parameters has on the outcome. So this is the total deformation maximum, and it seems to be affected the most by the frame pipe width. So that's the thickness of the front half, and that's having a very big effect, which is good. So maybe for my next optimization run, I'd make that wider than it is as a starting point. Same goes here. So the left chainstay radius is having a big effect on the axial force maximum, which is to be expected because as you increase the stiffness of the outside chainstay, the one that's not directly taking load, you'll expect it to take more load. Yes. And then, so our geometry mass is obviously positively affected by the thickness of your tubes, and here the maximum stress is inverse to all of them. So as you get bigger tubes and thicker tubes, the stress goes down. So go ahead and do an optimization, do a few iterations, and find the best possible concept for your geometry, and call over a tutor once you're done to have a look at what you've created and have a talk through.